Hello there everyone, I'm Crazy Caleb, and today I am excited to bring you a highly requested tutorial of hereditary base notation. Let me turn down the volume real quick of this music, so we can focus on the module. So, what this module does is we have a number that is supposed to be given to us, and what it says here, the bottom display shows a non-hereditary base n number where n is a number ranging from 3 to 7. So what we need to do is essentially do some calculations with this number, and you'll see what I mean later, and then input it back into another base. So there's going to be a lot of base conversions. So yeah, so we will use the BOM and its edge work and count the number of true statements in the table below and determine what base value of k is. Now, what does k have to do with anything? We're supposed to be looking at base n. K is the answer that is required to be submitted in. So base k is what we must submit our answer in that we get from our calculations. So before we get into the main work of it, let's grab our edge work because all of this will actually be relevant. So we have 5 batteries and 3 holders, a lit SIG, plate RJ RCA PS2, plate RJ DVI, serial number of 3 Zulu 3 Bravo Golf 2. Just make sure that's it. That it is. And let's also grab our number from the display. So we have 102 4402. So let's go through these statements. Let's figure out what's true and what's not. Lit FRK present? Nope. Last digit of the serial number is odd? No, it is even. There's a 2. First digit of the serial number is even? No, it is odd. It's a 3. An unlit SIG present? We have a lit SIG present, and that is it. That is not true. More than 36 modules? Nope. That's hereditary on the BOM. Exactly 1 module with a forget in its name? Nope. The first 2 characters of the serial number are letters? No, there is a number in the first position. A lit indicator Bob is present? Nope. Unlit IND? Nope. More unlit than lit? No, we have 1 lit and 0 unlit, so that's not true. The initial time is 15 minutes or less. We have set our timer to 60 minutes, so that is not true. There are ternary converter, Simon stores, or ultra stores modules on the BOM. No, this is our only module on the BOM, so that is not true. There are more than 4 batteries on the BOM. This is true, as we have 5 batteries and 3 holders. Speaking of the next rule, there are 2, 3, or 5 battery holders on the BOM. That is true. We have 3 battery holders, so that applies. There are basis or indigo ciphers modules on the BOM. No, there are not. There are exactly 2 digits in the serial number. We have 1, 2, and 3. No, that is not true. Serial number contains any letters from Goodstein. There is a G right here, so that is true. There are more than 2 AA batteries. Let's take a look. 1, 2, 3, 4. That is true. So now what we will do is we'll take a look at these few conditions here. If the number is less than 2, then k would equal 10. That is not true. We have 4 conditions that are true, and it says here if the number is more than 16, then k equals 8. That is not true. So otherwise, k is the number of true statements. So base k is going to equal 4. And this is the answer that we must submit in. So now, taking a look down here, let's try and figure out what our number n value is determined by. So n is determined by 3 plus the number of indicators. So we have 3 plus 1 being 1 indicator, present, the lit SIG, and the last digit of the serial number, plus 2. We would subtract 5 from n until n is between 3 to 7. Let's take a look. 3 plus 1 plus 2 is equal to 6. So our n value is 6. Once the base n number is found, convert it to hereditary base n number. So let's do that first. Let's actually break apart this module. So how exactly does hereditary base notation look? Well, how does base writing look? For example, in 47 right here, in base 3, it would look like this. 1 times 3 to the power of 3 plus 2 times 3 to the power of 2 plus 2. And the way how this works is your base 3 powers would be equal to 3 to the power of 3 would be 27, 3 to the power of 2 would be 9, 3 to the power of 1 would be 3, and 3 to the power of nothing is a constant, so 0. So now, what we need to do is pull our handy-dandy calculator and see just how true this is. So, we would take 47, and then we would subtract as many 27s as we can until it goes below 27, which in this case, we can only subtract it once, and that gives us 20. Now let's move on to the next calculation. So we can now subtract 9, so minus 9, minus 9. We were able to do that twice, so that would be a 2. Next up, we write, next up, can we subtract 3 from our solution? That should be a 3, not a 0. Can we subtract 3 from our solution? No, we cannot. So that would be 0. And then we're left with this constant value, which is essentially going to be our remainder. So 2. So this would be base 47. This would be 47 in base 3. 1, 2, 0, 2. And that essentially equals the same thing as what it is looking like right here. And we can pop up a little base converter here just to make sure that that is indeed actually correct. 1, 2, 0, 2 from base 3 to base 10 is equal to 47. That is true. So now, how exactly does hereditary base notation work? Hereditary base notation, it applies an additional requirement that every number except the base of an exponent must be less than the base itself. What exactly does this mean? It means that essentially, if this were to be written in hereditary base notation, 47 in base 3, in hereditary base notation, that would look like this. So we would have our 2 to the constant value, like so. That would make sense. Then plus nothing for the 3 to the power of 1. Then we would do 2 times 2 to the power of 2 times 3 to the power of 2. And then we would do 1 times 3 to the power of 1x times 3 to the power of 1. Now, what I'm trying to say is that instead of this being 3 to the 3, we need to find a way how the exponent will always be less than 3. In this case, it would be 1x to the power of 3. It's still saying that it is 3 to the power of 3. It's just written in a different way, because we can't have there can't be a number greater than 3 present in the exponent. So if this was like written in 3 base to the 3 to the power of 3, this would not be acceptable in hereditary base notation. That just simply doesn't work. That's how the module works, but yeah. It can't be the same value as the power that's being multiplied here, and in the exponent. I hope that makes sense. This is kind of a harder module for me to explain, and within the examples provided, I feel that once we start going over this will be a little bit better. This example was kind of a wonky one, but just having a basic knowledge of how bases work will especially be helpful in this module. But let's actually do this. So let's break this apart. So our n, our base value for this is 6. Now, what I prefer to do generally is actually go from right to left, assigning each of these values bases. Our rightmost being the constant, which is a base of 0, which is a exponent of 0. So this would be 0, then we would do 1, then we would do 2, then we do 3, then we do 4, then we do 5, and then we do 6. And what all these mean is essentially these will be the multiples, these will be the exponents of 6. So this would be 6 to the power of 0, essentially. and so on and so forth. 6 to the power of 1, 6 to the power of 2, 6 to the power of 3, etc., etc. So this being our constant, we actually don't have to write anything for 6 to the power of 0 because 6 to the power of 0 is just a multiple of 1. So essentially it would be just 2 times 1, so 2. So 2 plus there is nothing in for base 1. Then we would go on next to say 6 to the power, we would do 4 times 6 to the power of 2. 4 times 6 to the power of 2. Then next we would do 4 times 6 to the power of 3, as we are at the third power base. Then we would go on to say 2 times 6 to the power of 4, since this is the fourth power of 6. Then next up, there's nothing in 5, and this is where hereditary base notation really kicks in. It would be then 1 times 6 to the power of, and looking at this example like we did before, it would be like, and it's expressed down here, 1 times 4 to the 1 plus 1. And that's how we would express multiple numbers. It can't be the same as the base. It has to be a different number. So this would be base 6. So this would be 6 to the 6 that we would normally write in base conversions. However, this does not work for hereditary base notation. So we would have to write 1 times 6 to the power of 1. So this is being, this is just saying the same thing as 6 to the power of 6, because 6 times 6 to the power of 1 is 6, and then 1 times 6 is 6. So that's essentially how the writing works. And then if we were to actually continue on, let's say there was another 4 at the beginning, that would be the 7th base. We would do 4 times 6 to the power of 1 times that by 6 to the power of 1. And then after that is all said and done, we would add another 1 to that base. And just to explain here, this is how it looks. This is how it would look in writing down here, this example down here. So that is how this is how this writing works, and it's a little bit of a complicated subject, and I'm sorry if I'm explaining this too fast. If you have any questions, please do not be afraid to ask. But writing all of this stuff out is essentially the same thing as it is right here. And it's essentially the same thing as saying 2, 3, 4, then 6 to the power of 6, then 6 to the power of 7. That's really it. The only difference is that we cannot have the same exponent as the base power. So let's get rid of this. This is not part of the answer. So now we've written our answer in hereditary base notation. This is what it looks like in hereditary base notation. So now, where exactly does the calculating come in? Where exactly does this all come together? So once the base n of the number is found, convert it to hereditary base n number, so we've done that already, and replace all of the base digits of n with the new digits of n plus 1. Now, what exactly does this mean? And this is why we've written it out this way, because if it was 6 to the power of 6, things would get kind of complicated. But essentially what we're going to be doing is replace all of the 6 numbers with new digits of 6 plus 1. So 6 plus 1 equals 7. So all of these 6s would be replaced by 7s. So let's do that. So 7, 7, 7, 7, and 7. 6 to the power of 1 and 7. And this even applies for the exponential value up top. If we happen to have cases like this, this part will get replaced too. As long as there is a digit that is what the base digit is, in this case being 6, that will be added 1 to. And then we will subtract 1 to the entire number and rewrite the number into hereditary base n plus 1 number. So all we need to do is essentially subtract 1 from the constant, boop, and that will be calling it good. So now that we've done that, that's all we need to do. If there was a case where the 0, if it happened to be 0 in the constant value, which I've had happen before, we would need to break this base apart by 1. So this would become 3, and then it would be broken apart into 6 to the power of 7 over 1, because that's the maximum amount, and then we would do, if this was 0, for example, and we just subtracted 1, it would be plus 6. But that is not the solution in this case. So let's go back to plus 1, and make this back to 4. So we subtracted 1 from our constant, and if you take a look here, we still have 4, 4, 2, and then 1, equaling each of the base values. So now, once the hereditary base n plus 1 number is calculated, which we have done here, take all of the digits in the hereditary base n notation and do the following. If n and k are both odd or even, in this case, that is absolutely true. We have 4 and 6. They are both even. Add all digits together to get the final number. Now, what exactly does this mean? This means essentially that we are just going to take all of these digits in here, completely disregard all multiplication and exponential values, and add them all up. So let's actually do that. It's really straightforward. So we do 1 plus 4 plus 7 plus 2 plus 4 plus 7 plus 3 plus 2 plus 7 plus 4 plus 1 plus 7 plus 1 plus 7 plus 1, giving us a total of 58. And this is all we need to do. This result will be the answer, and we will need to convert this result to the non-hereditary base k number, and submitting it will solve the module. So we found our answer, and this is in base 10. We need to convert it to base 4, not to hereditary base 4, just normal base 4. So now let's do our multiples of 4. So we have 4 times 4 to the power of 3 is 64, if I'm correct. Times 4, yes. We have 64, then we have 4 times 4 being 16, then we have 4, then we have 0. So now let's figure out how many times we can get 64 into 58. We cannot, because that is lower than that. So now, taking a look here, let's see how many 16s we can shove into the 58. So 58 minus the 16 minus the 16 minus the 16. We can put 3 in there. We can do 3. And then let's see how many 4s we can put in. Minus 4 is 2. And then we can take our remainder of 2 and make that our constant. So now, just to confirm, this would have an answer of 322 in base 4. Let's confirm that with our base converter. So we go from base 10 to base 4. Plug in 58, because that was our answer, and convert. And just like that, 322 is our answer. We will input that into the module, 322.
Is the right answer.
And just like that is a solved module. Now, I hope you guys understood that, because that this is going to take a lot of my voice. But essentially, we've broken this up into hereditary base notation. Hereditary base notation works as I described it, and but hereditary base notation works like this, where you break each of them apart into base powers of that base that we found, and then if it happens to go if it happens to equal the same as the base that we had before, it cannot be it couldn't have been 6 to the power of 6. So this is where the hereditary base notation came in. Because this essentially equals the same as 6 to the power of 6, because 6 to the power of 1 equals 6, and then 6 times 1 is 6. So it's essentially the same thing, but in a different form of writing. Hell, even let's go to the logging and just to give a better example of how the module looks in the logging. As you can see here, I'm going to open this up. As you can see here, we did 1 to the power of 6 over 1 plus 2. So as you can see here, let's convert them all back to 6s. 6, 6, and then this was a 2. So we had plus 2, and then we had 4 times 6 to the power of 2. Then we had 4 times 6 to the power of 3. Then 2 times 6 to the power of 4. And then we had to get to the wonky part of 1 times 6 to the power of 1 times 6 to the power of 1. And then we did all of the adding of the bases. So we had 7, 7, 7, 7, and 7. And as you can see, it does change it up in the top part of the base, right there. Of the top part of the exponent, right there, as well. And then we ended up subtracting 1, like so, subtracting 1. And then all we had to do was add up all of these digits, respectively. All of the digits, even the powers, are added up. So, I hope you guys understood that, because that... It's a hefty module, and it's definitely an interesting concept to learn, I will admit. I struggled with this for a very long time. But good news is, I have a couple more examples in me, so let's go over, because there is another case that I want to represent, because this is also a little bit more confusing. So, our number for this time is going to be 2, 1, 1, 2, 1, 0, 1, 0. And I already have a pretty good idea that this is going to be in base 3, just from the looks of it. So let's grab our edge work for this time as well. So we have a lit FRK, lit FR Quebec. Was that a lit IND? Yes, it was. A lit IND. Plate DVI, RJ RCA, plate DVI RCA. And a plate empty as well. As well as a serial number of 0 Indio 1, Foxtrot Papa 7. Alright, let's take a look at this other example next. Refresh the page. We have a lit FRK present. Yes, we do. Last digit of the serial number is indeed odd. First digit of the serial number is indeed even. That is a 0, not a 1. Unlit SIG present? Nope, there is no unlit indicators. There are more than 36 modules? Nope. Exactly one module if they forget its name? Nope. First 2 characters in the serial number are letters. No, they are not, because we have a 0 right here, and that already cancels it out. No lit Bob, no unlit IND. There are more lit than unlit, so that's not true. The initial time is still 60 minutes, so that's not true. This is the only module on the bomb, so it's irrelevant. There are no batteries on the bomb, and there are no battery holders as well. There's no other modules besides Hereditary on here. There are exactly 2 digits in the serial number. No, we have a 0, we have a 1, and we have a 7. And serial number contains any letter from Goodstein. That is true. So, because we have a in India right here. And finally, there are more than 2 AA batteries. We have no batteries, so K in this case would equal 4 again. So now, next up, let's calculate our N value. N is determined by 3 plus the number of indicators plus 3, and the last digit of the serial number being 7 plus 7. So adding all of this up gives us, let's find out, 3 plus 3 plus 7 is 13. We're going to modulo 5, subtract 5 until in between 3 to 7. In this case, minusing 5 and minusing 5 gives us the value that I expected from the beginning of 3. So our number displayed on the module is in base 3. So now, here's where things can get a little bit complicated, especially with this module. So let's scroll up. So now let's separate how these bases work. So we have 0, then we have 1, then we have 2, then we have 3, then we have 4, then we have 5, then we have 6, then we have base 7. Lots of bases that we're going to be converting here, and this is where things get a little complicated, and it's good to have, this is why I break it apart in separate lines, because it's just easier to visualize and break apart the bases and understand what you're talking about. So we have no constant value. Next up, we have 3 to the power of 1. That's going to be happening once, so it's 1 times 3 to the power of 1. Nothing for the second exponent. And now we're entering into the point of no return, as I prefer to say. So now we have, this would be, as normal base conversion would say, 3 to the power of 3. That would be how it works. So it would be 1 times 3 to the power of 3. But according to hereditary base notation, that is not allowed. So here's where we get to the fun stuff. So that's going to be 3 to the power of 1 times 3 to the power of 1. Mark that with the notation. And that's going to be it for that submission, that conversion. Now, here's where things get even more interesting. So this would be 2 times 3 to the power of 4, and how exactly will we represent that? So we have 1 times 3 to the power of 1, timesing that by 3 to the power of 1, that's the same thing as base 3, and then we're going to add on 1 to that. That's as straightforward as that. This 3 to the power of 1 is completely separated from this 1. As a matter of fact, I'm also going to mark that off just to make it a little easier to visualize. And that's essentially what we're going to be doing. So now that was times that by 2, correction. And then next up, we're going to go to base 5. So 1 times 3 to the power of 1 times 3 to the power of 1 plus 2 in this case. And remember, we're still not above the 3 to the power of 3. So we're still sitting really nice right now. If we were to have plus 3 at the end of this, we need to change this multiplication value right here, which we are actually going to do in the next stage, which is going to be 1 times 3 to the power of 1, 3 to the power of 1 times, no, 2 times 3 to the power of 1, and that is it. So what exactly did we just do? So this would have been 1 times 3 to the power of 5, because 3 times 3 to the power of 1 is going to be 3, timesing that by 1, adding 2 to that would be 5. Now, essentially, we're at base 6, and then that's going to be 2 times 3 to the power of 1. 3 to the power of 1 we said was 3, timesing that by 2 equals 6. So it's essentially the same thing, but just in a different writing. Let's continue on to our final base power being 2 times 3 to the power of 2 times 3 to the 1 plus that 1. So same thing that we did last time with this, whereas 2 times 3 to the power of 1, and then we're adding on that additional 1 right here. And this is what it looks like in hereditary base notation. So now what we're going to do is we are essentially going to do the same thing that we did again. We're going to replace all of the base n digits, so we're going to replace all of the base 3 digits with the new digits of n plus 1. So we're going to add 1 to each of these base 3 digits. So all of these are going to become 4s, as well as the values in the exponents, since these are all revolve around the bases. Okay, that step's done. And then subtract 1 to the entire number. Now this is where I mentioned this where things can get a little nasty. Thankfully this is only 1 power away, but what we would essentially do is we would subtract 1. However, subtraction is not going to work in this case because we don't have anything to subtract from. So we need to break apart one of these bases from below to make it available to be subtracted from and actually work. So this is now, in this case, 1 times 4 to the power of 1. So this is essentially 4 in this case. So we can actually just say that this becomes 4, we get rid of this, and then 4 minus the 1 is going to equal 3. So we've basically said that this value is the exact same as writing it in the language of 4. So we've created our constant value to make sure that we can actually subtract the 1. And that's how this module is going to look now. And now that we've figured out what we've and now that we've gotten to this step, we now have to figure out what we have to do for the equation. So if n and k are both even or odd, add all digits together to get the final number. We do not have that case. We have an even and an odd. Base k has to be submitted in 4, and we have it in base 3. So otherwise, we're going to take the sum of all digits equal to n plus 1. In this case, n plus 1 equals 4. N plus 1 equals 4. And multiply it with the sum of all digits not equal to n plus 1. So what this is saying is we are going to take the amount of 4 in this display, add it all up together. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. So we have 10 4s, so we can do essentially 10 times 4. 10 times that by 4. And that would give us a sum of all of the 40s, of all the 4s in here. So 40 is going to be our sum of the n plus 1 digits. That is true. And we're going to multiply it with the sum of all the digits not equal to 4. So we are going to add up all of the other digits in this equation, I wouldn't say equation, but in this hereditary base notation writing, that aren't equal to 4. So in this case, we would add 3 plus 1 plus 1 plus 1. We've completed the first row here. Plus 2 plus 1 plus 1 plus 1. We've completed the second row. Plus 1 plus 1 plus 1 plus 2. We've completed the third row. Plus 1 plus 2 plus 1. We've completed the fourth row. And then plus 2 plus 2 plus 1 plus 1. And I'm just going to make sure that I added these up right. But if this was, but now since we've added all of these up, they equal out to be 26. So 40 times 26 is what we're going to get our answer to be. And I'm just going to make sure. I'm actually going to write this out. 3 plus 1 plus 1 plus 1 plus 2 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 2 plus 1 plus 2 plus 1 plus 2 plus 2 plus 1 plus 1. Let's copy and paste all of this into the calculator just to make sure. Oh, Control Z. Control C, Control V equals 25. Where'd I go wrong? Hold on, let's see. 3 plus 1, 1, 1. Then 2, 1, 1, 1. Then 1, 1, 1, 1, 2. Hold on a second. I'm better off just doing it again. Hold on. Clear. 3 plus 1 plus 1 plus 1. First and second row completed. Plus 2 plus 1 plus 1 plus 1. Third row completed. Plus 1 plus 1 plus 1 plus 2. Plus 1 plus 2 plus 1 plus 2 plus 2 plus 1 plus 1 equals 26. I'm going to go with that answer, and I'm going to pray to God that I did it right. So what we would do is we have found both of our sums, and we're going to multiply both of these together to create a very large number. And if the result happened to be above 8,000, we would modulo the result by 8,000. So 40 timesing that by 26 is 1,040. And this is our answer that we must submit in base 4. Okay, here we go. Ignore any digit 0 as it will not be used in any calculation. So that's just how it works. So what we have here is we need to find our powers of 4. So we did 4 times 4 times 4. The 3 to the power of 4 is 64. And we times that by another 4 is 256, which I think is going to be our highest value. Times that by 4 just to make sure. Oh no, we have another one. 1204, which is 1, 2, 3, 4, 5. This is 4 to the power of 5 here. And next up, divided by 4, would be 256. That's 4 to the power of 4. Divided by 4 is 64, then we have 16, then we have 4, then we have the 0. So 4 to the power of 3, times that by 4 to the power of 2, and then 4 to the power of 1, and then 4 to the power of 0. So that's how it works. So let's see how many of these bases we can fit into each of them. So we have 1040. Can there be a 1024 in subtracted from 1040? Yes, that is true. That is going to be 1 power, because we subtract 1024. It gets us a value of lower than 1024. Can 256 go into the solution afterwards? No. Can 64 go in? Nope. Can 16 go in? 16 goes in perfectly, so the rest of these are going to be 0. So minus the 16 is equal to 0. And just to make sure, let's go over to base converter. So base 10 to base 4 of 1040, convert it, is 100100. So this checks out, and this is our answer. So 100100, submit. Good game and extraordinary. Now I'm going to pull up the log file one more time just to give you an example of how this logging looks, because this is one of the weirder versions of logging that you'll get, or one of the weirder versions of hereditary base notation that you can get. So taking a look here, as you can see, we have gone through here. So so this would be, let's start from the end. So we had base 3, so there was no constant value, and it looked like 1 to the power of 3, which is true. And I'll actually leave this for you guys just to look at, but it's just how this looks is kind of weird. But after a while, once you understand the concept around it, you'll get used to it. It's really not that bad of a concept, trust me on it. So, yeah. Let's take a look at one final example, and please, if you guys have any questions when you're in the comment section, do not be afraid to ask, because this is not that really hard of a module. It's just really tedious, and the manual, in my opinion, does not explain it the best. So, let's continue on with one final example. I'm going to do this one a little bit faster just because I've done this module a lot. So let's go through it. And as always, thank you guys for actually wanting to see this module tutorial. I've been kind of wanting to do this one for a while. I just haven't gotten the time around it, and I actually didn't know how to do this module beforehand, but now I do. So let's put it down. Let's take a look at one final example, and let's hope this goes well. So we have 5 batteries and 3 holders, an unlit car, unlit SMD, and a lit FR Quebec. Victor Papa 2, X-ray Papa 1. Apologies if my voice is a little weird. I've been recording tutorials for like the past 2-3 days, so talking a lot has kind of degraded the quality of my voice, I guess I would say. Let's go through our truth tables, and that's actually pretty much all we need from the module. Alright, so we have more unlit. Nope. Yes. Yes. No. 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 Yes, they are. They're actually that. Okay. More unlit than lit. Nope. Nope. That is true. That is true. Nope. Exactly 2 digits. Good Stein. Nope. More than 2 AA. That is true. We have a lot of truth indicators this time. Okay. Interesting. 1, 2, 3, 4, 5, 6, 7, 8. So our base K, our answer is going to be in base 8. Our N value, let's go down here. So we start with 3. We add the amount of indicators, being 3. And we have the last digit of the serial number, which equals up to be 7. So now we know that this was in base 7. This was actually pretty easy to identify just based off of from the module. It has to be in the range between 3 and 7, and no number can go above 7 because bases work as a 0. In this case, base 7 has the numbers 0 through 6. So that's how that works. So let's continue on. So we have base 0, we have base 1, we have we have 2, we have 3, 4, 5. I'm essentially just assigning the exponential values to each of these numbers. And this is actually a really easy example because we won't have the hereditary base notation kick in that much. So we have 4 plus nothing from 7 to the power of 1 or 7 to the power of 2. Next up we have 6 times 7 to the power of 3. Then we have 5 times 7 to the power of 4. And we have 5 times 7 to the power of 5. Notice how none of these notice how none of these exponents go above 7. So we are good, and we do not have to write hereditary base notation. So now we are going to be using the following. Let's increase all of the 7s by 1. So these will be 8. These will be 8. These will be 8. And now we will subtract 1 from our answer. It's important to note that we will always increase the bases first and then subtract 1 afterwards. So 3. And now we just perform our magic. If n and k are both odd or even, they are not. We will take the sum of all digits equal to 8 and multiply them with the sum of the digits not equal to 8. So we have 8 plus 8 plus 8. 8, 16, 24. So 24 is our first number of the n plus 1 digits. And now we need to add the rest of the digits and get our multiplication value. So we have 3 plus 6 plus 3 is 5 plus 4 plus 5 plus 5. And that is equal to 31. So all I did was just avoid the 8s for the second part of this equation. So 31 is our answer. So 24 times 31 is equal to 744. Now, this is our answer in base 10, and we need to commit it. We need to convert it to base 8. So let's do that. So our powers of 8, so we have 8 times 8. 8 to the power of 2 is 64. Let's try and multiply by one more 8 and see where we go. 512. 512 is going to be that, and then 64, and then 8, and then a 0. That's pretty much as high as we're going to get, so I know that for a fact. So 744, we can subtract 512 from it, so that's going to be 1. Let's see how many 64s we can get rid of it. Minus 1, 2, 3. That's going to be 3. Let's see how many 8s we can subtract from it. So minus 1, 2, 3, 4, 5. And that is perfect. 1350 is going to be our answer. And just to confirm, 744 in base 10 to base 8 to base 8 converted is 1350. That checks out. Submitting it into the module. Submit it. And just like that is a solved module. Please, if you guys have any questions, do not hesitate to ask them in the comments below. This concept was definitely one that I was very hesitant on making, just because I personally did not know how to explain it that well. I hope I did. I hope I did my job, and I hope you guys actually enjoyed this tutorial. Remember to stay crazy, stay cool, and I will see you guys later. Bye-bye.